Hello. So today I'm gonna be going over how to how to derive, integrate vectors. So the best way to put it all together with derivatives and integrals is by doing a motion type of example. So, for example, if somebody kicks a soccer ball and there are certain forces. So now I'm asking, oh, okay, so what is the position of the object? What is the equation of the object in vector form? So in here it says that soccer ball hit is a is is hit east with a velocity of 30, 0, 10. So 30 meters per second in the east direction, 0 in um, the south direction, and then 10 in the up direction. So I'm gonna first draw the XYZ plane, I mean axis. So in here we have up, we have down, we have east, we have west, we have south, sorry, we have north. This is north. And then this is south. Okay, so we first start off with, oh yeah, sorry. And then it says a crosswind blowing south, creating an acceleration of this much. So let's first start off with the acceleration, and then we can build it from there up. So it's just like regular calculus 1, but except with vectors and except we're dealing with 3 dimensions. So the first, we have an acceleration. We want to create an acceleration vector. And then it just says a south -5 meters per second squared. So 0 horizontal. Yes, a y direction of -5, so -0.5, and then uh, actually another type of acceleration that's here on Earth and is 9.8 for the acceleration due to gravity. 9.8. So that's our acceleration vector. Now to make it into not to make it into a position equation, we need to now take the integral of this. So all I gotta do is to find the integral of this. Is say that the v vector, spread in terms of t, is equal to the integral of this vector. So now this is actually pretty straightforward. All you have to do is take the integral of each component one at a time. So this is going to become the v of t is going to become, so the integral of 0 is just 0, 0, and then this is negative, so -0.5 t, and then 9.8 t plus c. Okay, so we do have so the plus c is maybe some type of initial condition. And we do have an initial condition. It says that the velocity is this, 30, 0, 10. So all we have to do is replace this with this. Because if you think about it, so the initial position, so if we plug in 0 for each of them, this will become a 0 vector. So now, if we combine all of this, we can have this thing. The true V equation is going to be 30 -0.5 t plus 0, so we can just get rid of the plus, and then 9.8 t plus 10. and then that's our velocity. So now again, we want to integrate it. So all we gotta do is just take the integral of this dt to find our position. So again, so 30t negative 0.5 t squared over 2, and then I don't know, we're doing it one at a time, and then 9.8, so 4.9 t squared plus 10t. Okay, so what is our initial condition? So it doesn't say that it starts off anywhere. If it said, oh, it started up maybe 5 feet or something like that, then we will have to add it. But there's none, so there's technically a plus c, but if we plug in 0 for everything will go away. So this plus c is just, it's not really needed, because the initial condition, there's no really, the initial condition is that it's at the origin. So that's our equation, our position equation. So now maybe we want to sketch where this is, right? So all we gotta do is take see where this is. So at time 0, so when z is 0, right? So when this is 0, we have these components, and then we want to, okay, sorry, we want to see the soccer ball is hit in a east direction, so it's definitely going to be towards this direction, correct? But then it says that there's a south wind creating it, right? So it's going to be blowing it south, so it's going to be towards this quadrant. So it's going to be in this quadrant, and because it's going up, and this is just a parabola, so technically it's just going to go like, oh, and I'm sorry, I forgot to mention something. So this should be a negative, because the force of gravity is towards the negative direction. So this is all negative, which makes sense, because then this should be like this. Okay. So that's good. So now we want to maybe answer a couple questions. Maybe determine the time, of flight and the range. Of the ball. Okay, so maybe the first thing that we want to see is how long was it in the air, you know? So determine the time of flight. So all we gotta do is try to find when this thing is equal to 0. And then we're gonna find how high it is at that particular time. And then because it's symmetric, we can multiply it by 2. So all we need is actually the z component. So we can pull out the z component. I can just call it z of t is equal to 0, because I'm going to try to find when this thing hits 0. So yeah. So when the z is 0, that means it's going to be 0 here and here, right? Because we're pulling it out of the position equation. So if I set equal to 0, 0 is equal to negative 4.9 t squared plus 10 t. So you see we can factor out a t, so we got negative 4.9 t plus 10 t. T is 0, which makes sense because that's one of our initial positions. So now we solve it for the other equation. We say that t is 0, and so we pull a calculator. Ten divided by 4.9, we get a time of 2.04 seconds. So that's how long it was in the air. Okay, so now the next question is the flight, determine the range, right? The range of the ball. So now all we have to do is to plug this time into our formula. So, sorry, let me check something. Yeah, so if we're trying to pretty much figure out the overall range of it, all we gotta do is find we have to find the magnitude of it, of the position. So how do we find the magnitude? Well, remember, it's just the distance. So r t, and because we know the maximum time, all we have to do is plug this time into here, into the t's, and do it from there. So we can do 30 times 2.04 and we have 61.224 squared plus, so now we plug it into our other equation, so we got negative 0.5 times the time that was given squared divided by 2. We get a negative 1.04, but when we square, it's just going to go to positive. Then plus, so now we got the other component, negative 4.9 times the time squared plus 10 times the time. Oh, I get 0 for it. Yeah. Okay, so I get 0 for it, which makes sense because we're trying to find the component that lands in here. Yeah, in here, right? So there's 0 z component. So that makes sense. So then so now we can take this and compute it. And I get an answer of 61.23 meters. Okay, so now all we gotta do is find the maximum height of the ball. That's the last part. So max height. So how can we know that? Well, the max height, if you remember, is just the derivative of the position in the z direction. So what we have to do is take the z component of the derivative of the position, set it equal to 0. That's negative 9.8 t plus 30. Oops, sorry, not 30. It should be 10, right? Yeah, 10. 10. And then with that is gonna, once we isolate for t, is gonna give us the maximum time, right? It's gonna give us the maximum. It's gonna tell us the time where it's at its maximum. So 10 divided by 9.8 gives 1.02. That's the time in seconds. So now we have to do is plug it into the regular z component this time. So negative 4.9 times 1.02 squared plus 10 times 1.02. So if we do this, we get a total height of 5.102 meters, which is not very high. Okay, so last thing I want to point out is that once we how we took the integrals of each component, that's how you take the derivative of every component. Kind of straightforward. And then the limit is the exact same thing. If you want to take the limit of the whole vector, you got to just do it component at a time. And you want to find the magnitude of it, you just take the distance formula. And overall, that's it. So next time we're gonna be going more in detail about different types of motions and things that that can happen, such as curvatures. We're gonna go over a lot of curvatures, torsion that can be done with these vectors. And overall, yeah, that's